Okay, so we're going to move beyond simple material balance problems where we've just looked at one unit where we may have multiple inlets and multiple outlets going into one particular unit, whether that unit's a mixer, a separator, what have you. And we're going to look at cases where we may have multiple units. So, for instance, in a real chemical plant, we'll have lots of different units and so forth. So we have here, you know, simple case, and then we have a multi-unit case where we have multiple units that are involved. We may have all sorts of streams going all different directions and so forth, and that's what we want to really get into, because this again is what most of real chemical engineering is like. And so the principles of solving these systems using material balances and the equations and so forth are all the same as what we've learned with the simple systems, but we just have to pay attention and learn a few more tricks. Here is a multi-unit process where I've just drawn, and this is actually taken from the book, Feller-Rousseau and Boulard book, where we have various feeds. We have one feed here, and they mix at this point and then enter in this, what we call unit 1, and unit 1 separates some as product 1, some of it continues on, and we take some of that off to this product 2, some of it goes on to unit 2, and then we have another feed, and then product 3. So we have this complex mixing and separating processes going on. Now we want to be able to set out our equations and so forth, material balance equations, to go ahead and solve this. And to do this, we really need to understand the concept of a boundary. And when you have large complex systems, you've got to pay attention to those boundaries. And the boundaries will help us define what material balance equations we'll use. So for instance, let me just draw a little red circle here around this boundary. So what I've drawn is this circle around this little mixing point right here, where we have feed 1 and feed 2 coming in to mix to form this combined feed here. And this red circle here represents the boundaries which way we can do material balances on. So for instance, if I were to look at the material balances around this little red circle here, I would have the feed of 1 plus the feed of 2 is equal to the, what I'll call, mixed feed. And the mixed feed right here is what's actually going into what we have labeled there as unit 1. And so I can write out the material balance equations around this boundary here, or around this little part right here that I've shown you here. And you know, if there's multiple components, I might have multiple material balance equations, one for each component. I'll have the total material balance equation, which is more or less what I've written here. And that's the material balance equations that I could get by drawing a boundary around this mixing point and writing them out. Now there's multiple boundary equations going on also. So for instance, I can draw a boundary around this point right here and consider what goes in at that separation junction. You know, we have here this coming in and these two streams coming out, and again I can write a material balance about inlet versus outlet for the total balance and also for each of the components. I can write out a material balance around unit 1. So in this case, I would have the mixed feed right here, this outlet feed here, and then the product 1 stream there. And I again could write out material balance of this going in is equal to this plus this. And that's what I'd have. I could also write out, or I could draw a boundary around unit 2. So around this unit 2 again, the inlet stream plus this inlet stream is equal to the outlet stream, and again we can write out material balances. Well, there's one other boundary that we can draw here, and that's around the entire system. So let me just draw around here. And in this case, if I do the material balances around the entire system, I would have feed 1 plus feed 2 plus feed 3 is equal to product 1 plus product, should be P there, product 2 plus product 3. And in the overall system, around this entire boundary, around the boundary that I've drawn here, none of the internal streams come into play when I'm writing out my material balance equation. So depending on what material balance, and depending on how I draw my boundary, that will determine what the material balance equations are. So for instance, when I'm drawing my boundary around this mixing point right here, I only have this inlet and these two outlets. All these other streams over here, feed 1, feed 2, product 3, feed 3, they have nothing to do with this mixing point right here. And those material balance equation around this mixing point does not have any of those variables in it that would be in that system. And that's a big part of doing these material balance equations, realizing that we can write different material, or that's the big part of these multi-unit material balance processes, is realizing that we can write material balances, many different types of material balances, depending on the boundaries that we consider. And now when we're doing a real problem, we usually don't draw boundaries like this, like I've shown with the red boxes and so forth. We certainly can. If you're working on a problem and you're not sure what material balance equations to write, by all means, draw some sort of boundary. Go ahead and draw some sort of dashed line around a unit in order to help you realize what's going in and what's going out in order to write out your material balance equations. But if we see a flow diagram in the book, there won't usually be these imaginary boundaries drawn. But again, if it helps you when you're writing out your material balance equations, by all means do it. But other than that, identifying our variables, drawing our flow diagram, identifying what we're trying to solve for our unknown variables, and then writing out the equations and then actually solving the equations, very similar to the process of solving when we are only considering one unit, when we have as opposed to multiple units. The multiple unit process is very similar. So there's our introduction to multi-unit material balance problems.